Have you ever used colligative properties to calculate molar mass and ended up with a number that seemed completely wrong? This happens when the number of solute particles changes due to dissociation or association, leading to what we call abnormal molar mass. In this lesson, we'll learn why this occurs and how we correct it using the Van 't Hoff factor, a powerful concept introduced in 1880 to bring accuracy back to colligative property calculations. Abnormal molar mass is a molar mass calculated from colligative properties that deviates from the true value due to solute dissociation or association. Colligative properties depend on the number of solute particles, not their identity. So, if a compound breaks into more particles or combines into fewer, the measured colligative effect changes, and so does the calculated molar mass. This leads to either a lower than expected molar mass in dissociation or a higher than expected molar mass in association. Take KCl, for instance. If we dissolve 1 mole of KCl, 74.5 grams, in water, it dissociates completely. KClK plus Cl, potassium chloride dissociates into potassium ion, K plus, and chloride ion, Cl minus. That gives us 2 moles of particles. If we ignore enterionic attraction, this would mean that boiling point elevation is equal to 2 times 0.5 to K is equal to 1.04 K. Now, if we assume there is only 1 mole of solute, we'd wrongly conclude that 74.5 grams produce 2 moles, giving a molar mass of 37.25 grams, which is half the actual value. This is a classic case of lower than normal molar mass due to dissociation. Now, let's look at association, where molecules combine instead of splitting. In benzene, ethanoic acid, acetic acid molecules tend to dimerize. 2-CH3COH, Dr, CH3COH. Due to hydrogen bonding, 2 molecules associate into 1. This reduces the number of solute particles. If all molecules dimerize, the number of particles becomes half. As a result, DTB or DTF becomes half of what it should be. The calculated molar mass appears to be twice the expected value. This is a case of abnormal molar mass due to association. To fix these discrepancies, Van 't Hoff introduced a factor, denoted by I, which accounts for the actual number of particles. The Van 't Hoff factor is defined as I is normal molar mass, abnormal molar mass, or I is observed colligative property. Calculated colligative property, or I, is total moles after association, dissociation, initial moles before change. If I is greater than 1, I greater than 1. Dissociation, more particles. If I is lesser than 1, I less than 1. Association, fewer particles. If I is equals to 1, I equals to 1. 1 arrow. No dissociation or association, ideal case. Example values. For KCl, the value of I approximately 2. For K2, SO4, the value of I approximately 3. For acetic acid in benzene, the value of I approximately 0.5. When a solute dissociates, breaks into ions, or associates, combines into larger units, the number of solute particles changes. Since colligative properties depend directly on the number of solute particles, this change affects the observed values like boiling point elevation, freezing point depression, vapor pressure lowering, and osmotic pressure. To correct this, we include the Van 't Hoff factor, denoted as I, in the standard equations. It adjusts the calculated property based on the actual number of particles in solution. Using I, we correct all colligative property formulas. Relative lowering of vapor pressure. P0 minus PP0 equals N times N plus N. Boiling point elevation, delta T equals I times KB times M. Freezing point depression, delta TF equals I times KB times M. Osmotic pressure, pi equals I times C times R times T. This adjustment ensures that calculated results match the true chemical behavior of the solute. Let's summarize. Abnormal molar mass arises when solute dissociates, e.g. salts, or associates, e.g. organic acids. It leads to incorrect molar mass values if left uncorrected. The Van't Hoff factor. I corrects this by accounting for actual particle count. Modified formulas help us accurately calculate colligative effects, especially for electrolytes and macromolecules. Real-life relevance. Explains why electrolytic solutions behave differently and helps in biochemical calculations.